So I'd like Orhan to come up. So somebody, I think it was Janet, called me and said, there's this guy visiting, Orhan. You know, I thought that was his last name or his first name, but it's really his whole name. I think he will always be known just as Orhan. So Or is just starting as a Pappalardo Fellow, and he's going to talk about from nuclei to neutron stars, shortwave fermion correlations.
Yeah, so thank you, Peter. So I'm going to talk about probing cold dense nuclear matter. And it didn't feel right starting a physics symposium in 2016 without talking at MIT about LIGO. So the biggest thing in my mind, I think everyone here can agree with me, happened in physics and probably in science this year is the observation of gravitational waves by LIGO. Everybody in the world know it. We basically were able to hear, in a sense, a measure of two black holes. And we all hope that this effort, which has a strong leadership by MIT, will lead to a Nobel Prize this year. But you might ask yourself, why am I, a nuclear physicist, even interested in this? And the truth of the matter is that if you look at these objects we have in our universe, which have a very massive gravitational interaction, then naturally we have black holes, which have a very large surface gravitational potentials. But the next big thing we have are neutron stars, and anything else is much weaker as far as its gravitational interaction. Now, personally, I find neutron stars very interesting. Neutron stars are basically this very compact object we have in our universe. It's composed out of mostly neutrons, hence the name neutron stars. But it has a small component of about 5% protons, 5% electrons. And the nice thing about it is that the density of the system, the distance between protons and neutrons in this neutron star is about 5 times more than the density of nuclei we have here on Earth. So these are basically the most massive dense objects we have with a nuclear interaction in them in the universe. So basically, the entire structure of neutron star is this delicate balance between the gravitational pole and the nuclear interaction, which breaks apart. So we have a system that couples gravity and nuclear interactions in the extreme conditions of very high density. Now, we've learned quite a lot about neutron stars in the last few years. We've learned that there are these very massive neutron stars that can reach up to 2 times solar mass, but in a radius of about 14 kilometers. And that's a big thing. We learned that when you consider how nuclei are formed, where we have all the elements in the universe which are heavier than iron, which are fundamental to us having Earth and being able to be here, it's coming from the fact that 2 neutron stars collide, they merge together, and in that process, we think we have the conditions that we need to form this heavy nuclei. And just generally speaking, this is the best lab we have to study gravity because it's the one place we have extremely strong gravitational interaction, but with with some matter in it. But to understand these things, to understand the formation of elements in the universe and the nature of gravity in very high field regimes, you need to understand the fundamental thing that builds this thing, which is cold dense nuclear matter. And specifically, you want to understand it in small gravitational fields. So that's the basic thing you start with, and you want to see how that might be modified due to the influence of gravity. So that's what I do. I'm an experimentalist, and I try to study cold dense nuclear matter. So the big question is, how do we sit here on Earth and try to experimentally probe the highest densities in the universe? So putting the universe in a lab, in a sense. And just pushing things together won't work. You'll heat up the system, and you won't be able to study cold dense nuclear matter. And the way we do it is by basically not forcing nature, letting nature do its own job and just being there to take the right picture. So what we do is we look at nuclei. We have a bunch of nucleons, and sometimes you have a pair of nucleons which are very close together inside the nucleus so that the wave function overlap. So we basically look for these temporal fluctuations of nucleons which go one inside the other. It's a rare process. It doesn't happen a lot. But if you find it, you can study about what's going on when nuclear matter is very dense. Now, in momentum space, you talk about basically looking for a pair of nucleons with very high back-to-back momentum and a small center of mass momentum relative to the rest of the system, where every time we talk about high and low is relative to the Fermi momentum of the nucleus. So how would an experiment like the experiments I do look like? Well, I'm looking for this object inside the nucleus. And the way we do this is a bit violent, but it works. We come in with a hard probe. We take a nucleon, we kick it out of the nucleus into a detector. Now, if I know how fast I kicked something and I know how fast it came out, I can subtract the two and know its initial momentum. Now, if this momentum was really high above K Fermi, it means that I think it had a correlated partner. The only thing this partner can do to conserve energy and momentum is recoil out into a third detector. So that's basically what we do. We break up a pair, detect both nucleons, and reconstruct the initial state. Unfortunately, we can't do this using soccer. So we do it with electrons or protons with few GeVs of energy, which means that the wavelength is small enough to actually see individual protons and neutrons in the nucleus and kick them out and try to understand what happened before I interrupted the system and broke it apart. So the place I do my experiments is mainly Jefferson Lab. It's a lab in Virginia. This is basically the highest intensity continuous electron beam with GeV scale energy in the world. It costs a few milliards to build, about 250 millions it costs just to run it every year. And what we have is basically an electrons coming out of here, accelerated, turned, accelerated again, and you can do 6 turns, and then electrons are set into one of 3 experimental holes here, or a 4th one here. And the nice thing about Jefferson Lab is that MIT is all over the place. So I work in all A, B, and C. Richard and Peter are working with the free electron laser here for the dark light experiment, and Mike Williams is working here. So there's a very big leadership of MIT in everything that has to do with Jefferson Lab. And this is an example of how hole A looks like, okay? So just to get a sense of scale, this is Einstein, okay? So this is the size. So these are quite big detectors. And what's going on here is that you have this huge hole underground where electrons are coming in, they hit a target, a bunch of things come out, but electrons that are coming out of a specific angle, or protons that are coming out of a specific angle, go through a series of magnets into these detectors that we build. And then we can use electrons to knock out protons and study things. But that's not enough for my experiment. I want to see the partner when I break up a pair. So I need another detector, which does not exist. So we build it. So we build 2 detectors, one for protons, which is basically a dipole magnet that bends protons and put them into some detectors, or a big block of plastic that detects neutrons. This is how it looks like. This is basically what I built as a graduate student. Again, Einstein, if he was my height, okay, so quite big detectors, which is the big fun part of our job, building these detectors from scratch. But remember this forklift operator when I show you some more pictures, because when he moved it, the experiment down, the detectors down to the hole underground, the forklift operator wasn't careful enough when he placed it on the ground, so half of the phototubes on the back planes just broke off. So we spent 2 years building a detector, calibrating it, and 1 long weekend holding it together with rubber tapes. But the experiment went very well. We had lots of fun doing it, maybe some extreme. But eventually, we got some good results. So this is a kind of a collection of papers and results we got from these experiments. The first experiment was done on nucleus, which is carbon, 6 protons, 6 neutrons. And it was published in a series of papers. The last one was a science paper in 2008. And this paper taught us quite a few things. One is that whenever we knocked out this high momentum proton, there was always a partner coming out. So really, nuclei have these high momentum guys. They're very close together, and they come in pairs. So good, we can study something about them. But the reason this got into science and made a big noise was that the decomposition of the pairs, the ratio of proton-proton to proton-neutron pairs, was about 20:1. So this is what you see here. We got about 20 more proton-neutron pairs than proton-proton pairs. Now, this is not trivial. This is not something you get when you consider your textbooks, nuclear physics that you learn as an undergrad. And we understood it as from the fact that if you look at the potential, the interaction between 2 nucleons as a function of the distance, it has some attraction at large distances and repulsion at short distances, but it has to go through 0 at some point, and then sub-leading terms become dominant. Things we usually neglect are actually important, and that's what happens here. We have an interaction which we call tensor interaction. That's something that wants to take protons and neutrons which have the same spin, and as we all know in quantum mechanics, you can't take 2 identical particles, put them together in the same state with the same spin. That violates the Pauli exclusion principle. So it has to be 2 different types of particles, protons and neutrons. Then we said, okay, if that's the case, when we look at pairs which are closer together, we'll have more proton-proton pairs because that part of the interaction doesn't care about it. We saw it. And then in my PhD work in 2014, we published a science paper showing that this neutron-proton dominance, unlike what most theoreticians thought, continues to prevail all the way up to lead, a very big asymmetric nucleus. So the bottom line is that we see these density fluctuations, which are proton-neutron short-range pairs, in all nuclei, basically from helium-4 all the way up to lead, and we understand the nuclear physics that drives it. So the big question is, who the hell cares? So that's kind of how I feel when I sometimes hear other people talk about the tiny little details of what's going on in their field. So I'll show you why you care. Thermodynamics of neutron stars. So neutron star is mostly neutrons, a little bit protons, right, at practically zero temperature, which means that if you look in momentum space, these are what we call Fermi spheres, protons move very slowly and neutrons move much faster. But now if you introduce these correlations, what you do is you get fast neutrons correlating with slow protons, heating up the protons. So the entire thermodynamics, the heat that you have, the velocity that you have in protons and neutrons could be drastically modified because of this effect that is not being taken into account in most calculations. Then if you just think about the general case of what happens when you have different types of fermions in an imbalanced system. So let's think of a dense body where you have, let's say in this case, more girls than boys. And in this specific body, for some weird reason, boys only dance with girls. Then what will happen is that the average boy will dance a lot more because there are more girls in the party. And that's what we see in this type of systems with short-range interactions. If you look at the distribution of the velocity of how fast particles are moving, the guys who are correlated, who are dancing, you have one proton and one neutron here. But you have more neutrons overall in the system, something like lead or a neutron star, so they have to occupy the low momentum states. So actually, there's a larger probability to be in high momentum for a minority in this system than a majority. And actually, when I came to MIT and showed it, I heard from the atomic people from Martin's ruling that they've known it for years, actually, in atomic systems, and they were right. Because this is a universal thing. This is not something that's unique for nuclei. It happens in any system you have in nature. And that's the strong thing. We find properties of nuclei, which are this complex, weird thing that we don't fully understand, which is universal and quite simple, which is nice. Then if you look inside the proton, then we know, like Jesse told us, that proton is made out of these quarks that we have and these gluons that bind them together and all sorts of other quark, anti-quark pairs, and the way we characterize the system is by looking at how fast these guys are moving together. And what we know is that when you look at the distribution of the partial velocity of quarks in a nucleon that is free and that is bound inside nuclei, in nuclei these quarks are moving slower. So you take a proton, it has some distribution of quarks, you put it inside nucleus, quarks in a sense move slower. And that's the rate you see here, that's the ratio, and it goes down, which means they're moving slower. That's called the INSEE effect. And the way I like to think about why this is such a big challenge, this has been discovered over 30 years ago and still people don't understand what's going on, is using this old fairy tale, because this is really a question of strength scales in physics, right? So we take a system and you put in an external field. And if it's a weak system, the external field will naturally affect its structure. But if it's a strong system, like this house here, the wolf can't do anything, right? And the thing about nuclear physics is that we know that these quark piglets are inside the proton, which is a very strongly bound system. So why should a weak nuclear field, 8 MeV, compared to a proton mass of a GeV, okay, so talking about a few orders of magnitude difference, why would that affect what's going on here? And so there are many works on this, but I'll show you our contribution. And this is this plot here. So this is how much a proton is modified when you put it inside the nucleus relative to how many short-range pairs you have in that nucleus. And without knowing too much physics, you can see that this thing correlates completely. So the more pairs you have, the larger the modification is on average. And we understand that this modification is probably more associated with these pairs of nucleons. And we had lots of work based on this, lots of theory work, et cetera. And we got the cover of the CERN Courier paper, which is this magazine that comes out of CERN telling everybody about the most exciting things that are happening in nuclear and particle physics. And when I was presenting this, I was told that this is as close as someone like me will get to getting the cover of the Rolling Stone magazine, which is a very nice thing to think about. But really, this made a lot of noise. So we thought about looking at other correlations. This is one between the total highway fatality rate and the amount of fresh lemons you import to the US from Mexico. So again, a nice correlation, which implies that Mexican lemonade saves lives, right? So correlation does not imply causation. That's the big message of this thing, which means that except for doing all the theoretical studies that we did, you need to do experiments. So I just want to tell you that we're building another set of big detectors that will study the internal structure of only these guys in a correlation, and will be able to tell us if our theory is correct. And when two nucleons are very close together, they overlap, the quarks start talking, and you have modification, which actually relates to a lot of ideas that came from MIT in the last 20 years from the theory side of things. So the last thing I want to tell you, without going into any details, is that we do these experiments, but the implications are huge. I gave you some example, but there are things related to astrophysics, to neutrino physics, to double beta decay, to atomic physics. Basically, all over the map, we have a nuclear system, a nuclear target, or some sort of a strong coupled system with a short-range interaction. These type of things are relevant. And we have papers actually on all of them, and the other groups have even more papers from them all put together. So this is also my summary. We do these experiments where we knock out these guys from the nucleus. I've shown you how they affect nuclear, quantum, and particle systems. And trust me, there's much more. I just want to emphasize the group. These are not things I do alone. And we have a very nice group of grad students from MIT and from Tel Aviv and our Dominion working on this, and they are really superb. Hopefully some of them will be future Pappalardo Fellows. And with that, I thank you, and specifically I thank Nii and Jane for an excellent fellowship and a great opportunity to be here at MIT and do all these great things. Thank you.
One of your earliest slides indicated that a neutron star is composed of 5% protons, 5% electrons, and the rest neutrons.
More or less, yes.
Pardon?
More or less. It's not exact numbers, but
I
yes.
get approximate. It doesn't matter. But in either case, I would assume a neutron star has if you plotted the force of gravity from the outside to the inside, it would increase significantly as you get closer to the center of it. And therefore, another slide you showed the protons, it appeared, I agree it's one-dimensional, being all the way through. And I would find that strange because I'm still assuming a proton is lighter than a neutron, and I wonder why that gravity differential doesn't force the protons to go more towards the exterior, perhaps similar to the electrons.
Mm-hmm. Okay, so you're 100% right in everything you said. But the situation is the following. So this plot that we showed here when we showed the protons in the center, this is in momentum space. So this is a velocity distribution indicating that the protons move slower than the neutrons. This is what we call a Fermi-sphere. Now, you're 100% right, and this is one of the big questions in neutron star structure.
You're going to give the answer. I give the question. Sorry.
So the question of how exactly the protons are distributed inside the nucleus is a very important one. And that's the basic thing that we're starting to talk about. That is what we call the symmetry energy. So actually I have a paper on that. You ask yourself, if you take a proton, if you take a system and you change a neutron into a proton, how would the equation of state changes, okay? And that is something that relates exactly to these things, because when you break the symmetry of the system, you have less pairs that you can create, and therefore you have less energy. So actually it's not so much the mass as it is the energy of the protons and the neutrons in the system. And there is a gradient. There is some gradient towards the entrance. And actually, in the core of the neutron star, we have no clue what's going on. Many people talk about it. They don't know anything about what's going on there, really. Nobody knows. But we do know that there's a gradient. And we have papers actually discussing how the symmetry energy changes because of this thing and how that affects the equation of state of the neutron star. And it's a paper that's about to come. There's a second paper about to come out exactly on that.
Send it to me so I could understand.
So we have someone actually who looks at neutron stars in the back of the room. Deepto, you had a question?
Hi. So MIT is hoping to construct an X-ray astronomy experiment called NICER, which will be launched on the space station next year. and its intention will be to measure, do accurate simultaneous measurements of masses and several neutron stars.
Yeah.
So getting to your radius A question, I was wondering, this proton-neutron correlation you're talking about, what kind of effect would you expect that to have on, say, neutron star radius? Would you expect it to have a significant, for given mass, a significant change in radius?
So if you would ask me 2 years ago, I would tell you yes, but now I would tell you no. So we did this study, and with the knowledge that we currently have, we do not see that they have a big effect on the overall equation of state, on the mass-radius relation. That's the paper I was telling you is about to come out. We worked with Andrew Steiner on doing fits of neutron star observables to see exactly when you put that in, again, with the knowledge we have so far, how that affects. And you can basically play with an interplay between kinetic and potential energy and keep everything the same. But it will have a big effect on what we really don't know, which is the cooling rate of neutron stars, because of basically Pauli blocking, which is broken off in this extreme scenario. And then you might have some direct Urka process and other things like that. So with what we know, cooling rates would be much more affected than equation of state. But there are many things we don't understand about the interplay between the kinetic and potential energy of these guys when they are formed and when they're broken apart. And the next generation of experiments we have will try to probe that a bit better. And with this insight, there could be a big effect. But at this point, we don't know enough.
So based on what you understand now, which way would you expect the cooling rate to go?
I wouldn't, based on what we know now, I don't think it will affect the mass radius connection. Oh, it would make the cooling faster. Yeah, and that's what we know based on observation compared to calculation. That's the direction you want to go in. That's where there's the discrepancy. But the question is how to quantify it. That's a very tough challenge.
So we'll find out in 2 years. We'll have you both back. Any more questions? Okay, I'll just.
Is there a temperature of a neutron star related to its mass?
Correlation between the mass and the temperature. Very weak, I would say. I would say very weak. Because it's the whole thing about the neutron star, it's a very cold system. So it cools down, but it's overall very cold.
Okay, I'll just mention, really, Rolling Stone, Wired. You want to get into Wired. Mark Kastner's been in Wired. Actually, the Hot magazine is probably something I've never heard of. So let's thank Ora again.
Thank you.